Yes, so we had still been discussing about stresses basically, or in stresses in particular, we had talked about the transformation of stresses, or we had discussed in length, in great detail, what is the reason that we want to be performing the transformation of stresses, ताकि हमें बहुत easily normal और shear stresses किसी भी plane पे पता चल सकें. और फिर we saw how actually in 3D या फिर in tensor notation how that stress transformation is performed. It's just this equation right here, that this new sigma in the new coordinate system is given by this q sigma q transpose. ठीक है जी, ये matrix या tensor multiplication से direct हमें मिल जाता है. A point ये है कि now we are moving on to more advanced things जहाँ पे we're not just going to be sitting around using our pen and paper and our own calculator to do things. The deal is that I'm not saying कि हम हर वक्त we do the 3x3 matrix multiplications ourselves. We should now move on to thinking for more complex problems. We're going to have to use tools, right? So it's perfectly fine if you use a calculator directly to do the 3x3 tensor multiplication, or you use MATLAB, or you use online calculators and so on, right? Because of course ये इतना straightforward तो नहीं है ना manually करना. लेकिन in any case, just do remember कि for simple cases we can do it ourselves. So इसी एक simple case को we had analyzed, which was the problem of stress transformation in 2D, and we saw कि इसी tensor transfer stress transformation से ही Mohr circle आता है. ठीक है, in undergraduate you have considered what the Mohr circle is, and in the undergrad we actually find this Mohr circle using equilibrium की arguments use करके, but they are completely equivalent to this thing of transforming the stresses using just tensor transformation. Right, so वो we saw कि it comes back to the Mohr circle in 2D. और उसी से फिर we had discussed that there are these certain important stresses which are our principal stresses, which are the maximum and the minimum of the normal stresses, or they're important because of course वो जो extremes हैं, that is the maxima and the minima of the normal stress at a point, उन्हीं से failure determine होगा. Right, so that's why it's extremely critical for us to be able to find these principal stresses. And as the name implies, वो principal stresses are actually the principal values of the stress tensor. So if we just use जो हम पहले ही consider कर चुके हैं कि एक tensor का कि principal values निकालते किस तरह हैं, then वही सारी operations apply करके on the stress tensor we can find our principal values. Please note कि it does not matter कि वो हम सिग्मा के ऊपर करें या फिर हम सिग्मा प्राइम के ऊपर करें या फिर हम कुछ सिग्मा कुछ और ओरिएंटेशन में करें, क्योंकि पॉइंट इज़ कि वो वही पॉइंट है, वो वही ओवरऑल स्ट्रेस स्टेट है. ठीक है, तो आप जब भी किसी भी ओरिएंटेशन के स्ट्रेस टेंसर से शुरू करें और यू फाइंड द प्रिंसिपल वैल्यूज़, वी शुड ऑलवेज गेट बैक दोज सेम प्रिंसिपल वैल्यूज़, राइट, बिकॉज वो उस पॉइंट का तो वही मैक्सिमा मिनिमा रहेगा ना, राइट. So that's one thing to remember. Secondly, also if the principal stresses are the maxima and the minima of the normal stresses. So if we represent our stress state using the principal stresses, then we just get the normal stresses as shown right here. I hope you guys can see this clearly. So as shown right here, तो वही stress state, ये वही point है, वही point in the body को अगर हम x1, x2, x3 में represent करें, so we get this stress tensor. Whereas if we reorient ourselves along the principal directions, the principal planes, then the stresses that we have remaining, या फिर the stresses that we have on those planes are just our normal stresses, no shear stresses on those principal planes. So we discussed all of these things, and then finally we moved on to talking about right, और ये इसका I didn't go into the long-winded three-dimensional proof of it. मैंने सिर्फ refer कर दिया था कि as was the case for our 2D problem, कि अगर हमें shear stress का maximum निकालना हो तो वो भी actually in terms of the principal stresses हम निकाल सकते हैं. Or what the straightforward, nice little, neat little expression is that the maximum shear stress that exists at a point is just equal to the maximum principal stress minus the minimum principal stress divided by 2. ठीक. So this is all that we had discussed. इसके अलावा just the side comments, a few side comments that I'd made were कि please be careful कि किस case में principal stress is important है, and in which cases it's the maximum shear stress which is important. It's determined by the type of material that we have. So just talking about the solid, like in solid mechanics, these are the different type of failure determines case whether the principal stresses or the maximum shear stress which determines failure. So for example, if we have ductile materials, then ductile materials ke andar it's the maximum shear stress which we need, and for brittle materials it's the principal stresses which are important. It's the tensile principal stress which is important to us. Okay? And that's because of the mechanism जिससे failure होता है. Brittle materials में fracture होता है, whereas ductile materials जो है वो plastically deform या yield करते हैं. Right? So this was all that we had managed to get till. So just a little recap. So now today I want to start off with the example that I'd left off last time. Just want to take a little pause right here and check, okay, was there anything which is still unclear from last time that you guys might be wondering about? No. Okay. So I'll move on. Right. So we've got this we've got this stress state given to us. So there's a point in the entire body. So matlab ye, okay, let me draw this problem out. So there might be some sort of a continuum body that we have, and then we're looking at one point. Okay. Or as I mentioned to you, can we just give like a generic stress tensor, then that we assume it to be the stress tensor in the XYZ coordinate. ठीक. So आम तौर पे ना जब अगर सिर्फ सिग्मा यूं ही given हो तो just assume कि it's in the XYZ coordinate system. So this would be X, this would be Y, and this would be Z at that point. ठीक है जी. So मतलब ये कि हम एक material element देख रहे हैं, infinitesimal material element like so, which is oriented along the X, Y, and Z directions. Perfect. So now what do we want to do? We want to find the principal stresses and the maximum shear stress at the point. Now that's pretty okay. Now we know, okay, principal stresses, they're just the eigenvalues, they're the principal values of the stress tensor. That's pretty straightforward for us, because all that means is, okay, sorry, my solve condition, that just means that we have to solve that cubic equation that we had. And I'm sorry, I don't expect you guys to memorize these things. I don't have it memorized either. So मैं probably गलती करूँगी, लेकिन let me write that down. So that used to be lambda cube. Maybe it's a good idea. I should just go back and see what it is. It's lambda cubed minus I1 lambda square plus I2 minus I3. Okay. Okay. Got it. Lambda cubed minus lambda squared I2 plus lambda I
I1 है पहले.
Sorry, I1 ठीक है. See, I अभी देखने में भी मुझे याद नहीं आ. Lambda I2 minus I3 is equals to 0. That's it. Where these I1, I2, I3 are the principal scalar invariants of our tensor. और in this case वो मैंने already लिख दिया है कि वो sigma stress tensor के क्या values होंगे, right? So I1 is just the trace of the tensor. So let's just find that out. So trace, of course, we know is the sum of the diagonal terms. So it's just I1 would be 50 minus 20 plus 10. So that is 40, of course. So we've got our I1. Then I2 is it's the sum of the determinants of the co-matrices within the tensor. Now remember, नहीं sorry, just note, you don't need to memorize this. ये तीनों और ये चौथा भी, which I'd forgotten to write down in this case, will all always be provided to us, या फिर we can look them up whenever we want to. So we don't need to commit it to memory. So I2 निकालने के लिए we do need to be careful को है क्या. So I think I'll do it ताकि we all get to practice it. So I2 is sigma 22 sigma 33 वाले का this thing, इसका determinant. Okay, so minus 20 minus 10 minus 10 10 plus sigma 1133 वाला, मतलब I'll write it down. So 50 20 20 10 का determinant, and then add on top of it sigma 11 or sigma 22 वाला. So this one 50 30 minus 20, or then just let's find what that is. So that would be minus 200 minus 100, इसका determinant आ गया, plus 500 minus 400. I really hope कि आप लोगों को determinants निकालने 2x2 matrices के याद हैं. अगर किसी को नहीं याद तो just okay, let me write that down. वो क्या होता था, A B C D का determinant जो है that's AD minus BC, just in case someone does not remember that. And then minus 1000 minus 900. So summing all of these up, we should get what the value is. It turns out to be minus 2100. Okay, so I2 भी आ गया. And then finally I3 is the determinant of the entire tensor. Now please, 3x3 matrices के determinants are a little bit more complicated. उसकी भी expressions हमें कहीं पे भी, मतलब if you just Google it, you will be able to find the expression for the determinant of a 3x3 matrix. Please note, as I always say, कभी जब भी थोड़ी सी maths वाली side आनी चाहिए, this is not, although it might be a maths heavy and notation heavy course, this is not a maths course. So please just use a calculator and directly find कि एक 3x3 matrix का क्या determinant है. And if you guys don't know कि वो कैसे करना है, determinant कैसे निकालते हैं calculators को use करके, तो just Google it and learn it, right? So don't go substituting into expressions and spending so much time doing that. Just directly find कर लें. Okay? So I have a calculator जिसमें ये हो जाता है. अब ये I know कि this is a little bit of an issue कि not every calculator is able to handle matrices. So I have FX 991 Casio का, forgot to say that. And that does do up till 3x3 matrix operations. Okay, और इसके अंदर हो जाता है. If you have FX 991, then you should be able to find a determinant, and higher than this, by the way. So इससे ऊपर जो भी होंगे वो सब कर लेंगे. I think मेरा पहला basic वाला था जिससे इसके आगे से है. So just please everybody check, ये आप लोगों के लिए task है, check कि your calculator is able to find a 3x3 matrix का determinant and is able to solve cubic equations, क्योंकि वो जो lambda cubed वाली equation है वो भी I don't expect कि आप लोग खुद solve कर रहे हो. Just solve it in the calculator. Or if you don't have a calculator that does it, then find out online के या फिर just use MATLAB अगर आप लोगों के पास MATLAB हो या Octave हो. ये इतनी सारी और sort of operations करने वाले software and tools हैं. ठीक है? So do take a look at this. अच्छा, इसी के अंदर let me show you a website that I like to use personally. I googled मैंने पहले directly, I don't know why I was doing that, but in any case, so this is a neat little useful website to perform matrix calculations online. So I'd recommend कि आप लोग इसको, अगर आप लोगों के पास calculator नहीं है तो इसको use कर लिया करें. ठीक? We can find the determinant. सबसे पहले find the inverse. transpose it, वो तो I think transpose तो हम खुद कर सकते हैं, I hope. And so on. So there are loads of useful things in here. So for us, this is useful. Find the determinant, find the inverse, kabhi, and so on. So anyway, so coming back to it, that is how I have just done it. I have just used the calculator to find I3, the third principal invariant. Right now, once I've got my principal scalar principal invariance, then I can substitute into our expression for the eigenvalues या फिर for the principal values and solve it. उसको solve करने के लिए भी again I just used my calculator. ठीक है, और calculator again fx911es या fx911 जो है they solve cubic equations as well. So yep, just straightforward doing that.
Excuse me, ma'am.
Yes.
मैम हमने चैप्टर नंबर 5 में किनेमेटिक्स में पढ़ा था कि ये I1, I2, I3 जो है ना इनवेरिएंट्स होते हैं, तो ये किसी कोऑर्डिनेट पे डिपेंड नहीं करते. तो वो मैम वहाँ पे तो समझ नहीं थी आई. वो उस वक्त आपने समझाया था तो वो अभी भूल गया, तो वो काइंडली इधर आप वो रिलेट करवा सकती हैं कि वो क्यों सेम रहते हैं.
बिल्कुल ठीक है, मैं अभी यही करती हूँ. जस्ट गिव मी वन मोमेंट टू जस्ट रैप अप कि हमने प्रिंसिपल स्ट्रेसेस निकाल लिए हैं, राइट, एंड देन आई एम गोना गो बैक टू इधर वही. आई हैव अ कमेंट अबाउट दैट, जस्ट गिव मी 1 second प्लीज. राइट, सो सॉल्विंग आवर eigenvalue equation, I've got the principal stresses that I need, right? अब please note कि ये lambda 1 even though लिखा हुआ है, this is the sigma 1, sigma 2, sigma 3, such that if I use my principal stress tensor के form में I represent that same stress state. वही point, वो क्या मैंने बनाया था, ऐसी कोई body थी, उसका ये point था ना. If I write down the stress tensor at that same point, but using the principal stresses, then mera stress tensor is this one right here. Why? Because we know कि जब principal stresses होते हैं तो principal planes पे कोई shear stress नहीं होता, सिर्फ वही normal stresses ही होते हैं. And that's why it's only the diagonal terms जिनके ऊपर हमारी वो principal values आ जाती हैं. ठीक है जी. अब बात ये है लेकिन कि वो पहले तो मैंने जो पहला वाला हमारा स्ट्रेस टेंसर था, दैट वाज इन द XYZ कोऑर्डिनेट्स, राइट. It was the stress tensor along these coordinate directions, whereas this stress tensor is along our principal directions. और आइगन वैल्यूज़ फाइंड करने से हमें वो डायरेक्शंस नहीं पता चलती, हमें उसके लिए हमारे आइगन वेक्टर्स निकालने पड़ेंगे. और that part of the course we're going to skip basically, because the point is now that you know कि the principal values या फिर the principal stresses are just the principal values. फिर अगर if you ever need to in your life also find कि वो directions क्या होती हैं, then I think कि आप लोग वो खुद ही आइगन वेक्टर्स को रिसर्च करके निकाल लेंगे कि एक टेंसर का आइगन वेक्टर निकालते किस तरह. बट लेट मी जस्ट अज्यूम फॉर नाउ कि मुझे पता है कि वो आइगन वेक्टर्स क्या हैं, सच दैट देन आई जस्ट वांट टू पॉइंट आउट कि ये सिग्मा प्राइम है अब प्रिंसिपल स्ट्रेस वेक्टर, दिस इज एक्चुअली द स्ट्रेस वेक्टर अलोंग सम अदर कोऑर्डिनेट एक्सिस which will be our principal directions. ठीक, it's no longer along the XYZ coordinate, it's along the principal directions. है वही point, है वही stress state, okay? है वही loading represent कर रहा. It's not कि कुछ चीज़ change हो गई है. It's just that we are viewing that same point in a different coordinate system. Right. Now, so अभी इसी से is related to the fact के what I'm sorry I didn't catch your name, whoever was asking. They had asked के this I1, I2, या फिर इधर से ही कर लेते हैं चलें. These I1, I2, I3s जो हैं, these ones. That these are known as the principal scalar invariants. अब ये बात है कि इनका नाम जो है ना, उनसे ही थोड़ी सी हमें हिंट मिलने लगी है कि ये क्यों, why are they called these things? ओहो, principal scalar invariants. So first of all, they are scalar values, that's why they're scalars. But the main thing that I want to focus on, क्या मैंने लिख दिया है? Sorry. Principal scalar invariants. The most important part of the word I skipped. So focus here please that these are invariants. Or what that this word is trying to represent is कि ये जो values है ना I1, I2, I3 वो आप जिस मर्जी कोऑर्डिनेट सिस्टम के अलॉन्ग ले लें मे बी ये एक्स वाई जेड था मे बी अब इसको मैं कोई एक्स प्राइम वाई प्राइम जेड प्राइम कह दूँ जिस मर्जी कोऑर्डिनेट सिस्टम के अलॉन्ग आप स्ट्रेस टेंसर को लिख लें इसके अलॉन्ग वो सिग्मा था इस वाले के अलॉन्ग वो सिग्मा प्राइम है if you find the principal scalar invariants for this and if you find the principal scalar invariants for sigma prime you will get the same values and that's what this invariant means that the value of these principal scalar values या फिर the value of these principal scalar invariants they are unchanged they do not depend कि हम उस particular property को किन coordinate systems में देख रहे हैं हम x y z में देख रहे हैं या x prime y prime z prime में देख रहे हैं okay let's try it out very quickly ठीक है let's try it out ये sigma prime किसी और coordinate system में है ना so why don't we let's find I1 I1 क्या था I1 was the trace of sigma prime ऐसा ही है तो trace क्या हुआ sigma 65.5 minus 37.1 plus 11.5 and if I do that I have a calculator with me by the way I came prepared I get a value of 39.9 या अल्लाह प्लीज़ मेरी इज्जत रख लें और ये 39.9 ही हो पिछला वाला yes it's 40 the 0.1 has disappeared in my rounding error so clearly ये जो lambdas की values थे I've rounded them right so I1 turns out to be this वो sigma के लिए it was 40 when I found it for sigma prime which I've written at some rounded values I get the same thing and if I try out the same for I2 जो अभी मैं नहीं करने लगी but I ask you चलें वो भी कर लेते हैं it's very easy right क्योंकि इसके तो छोटे छोटे हो गए ना that would be I'm gonna rush and do it very quickly 37.1 multiplied by 11.5 plus 65.5 multiplied by again 11.5 and then plus 65.5 multiplied by minus 37.1 and what do I get अगर कोई कर रहा हो if somebody has the calculator minus 2 so I'm getting minus 2103 point something something and again there will be a little bit of a difference owing to the fact that I made some rounding errors essentially but if I go back to the original I was getting minus 2100 so just proving what I was trying to show you that these values these I1 I2 I3 they remain unchanged whether we view it in this coordinate system or some other coordinate system that is they are invariant with respect to the coordinate system ठीक है जी और यही चीज़ I know I've discussed it a lot लेकिन I hope कि आप लोग just आप लोगों की उसी के लिए I have made a little bit of a comment in the slides as well ताकि when you come back a few weeks later on it आपको ये याद आ जाए बात if we find these same scalar invariants for some other orientation we will get the same value so for example इसमें I'd recommended कि आप ना इस stress tensor को rotate करें by 30 degrees वही जो stress transformation हमने करनी सीखी है और फिर find करें the scalar invariants and you'll see कि they will turn out to be the same and that's why they're principal scalar invariants okay okay thank you Mehta right now so we've got our principal values or we've got our principal stresses from that now we have to move on to finding our maximum shear stress right so I just want to remind you guys that इन्हीं से हमारे पास हमारा tau max आ भी जाता है. By the way, remember, tau represents the shear stresses. So tau max was sigma principal का max minus sigma principal का min divided by 2. So what is it? What is the maximum principal stress here? Someone tell me. Guys.
65.5.
Exactly right. It's 65.5. And what's the minimum?
Negative 37.1.
Perfect. 37.1. Cool. Perfect. So just solving this out, remember here that वो minimum ही है minus 37.1. Don't just take the magnitude. The minus is important, right? So then we can find our maximum shear stress, or just solving that through, it's 51.3. Okay. So if we have a ductile material, then this is going to be important for us, the shear stress. Whereas if we have a brittle material, फिर brittle material के तो लिए तो tensile का normal stress जो है ना वो सबसे important है. So it's this value which is most important. ठीक है जी. This is also important to note कि brittle material के लिए ये compressive stress is नहीं important. Minus represents compression, right? It's compressive normal stress. It's the tensile stresses which are important for brittle materials. क्योंकि उन्हीं से let's assume कि कोई brittle material में यू crack है, तो जब वो खिंचेगा, right, जब उसमें tension होगी ना उस crack के ऊपर, तो फिर ही वो propagate कर जाएगा through and it will cause failure. अगर तो उस पे, so this is going to cause failure, whereas if you have normal stresses which are compressive, which are closing this, फिर तो वो crack बंद हो जाएगा ना, तो फिर तो actually आसान हो गया काम. So be careful here as well, that just for your information, okay, it's the tensile stresses which are important for brittle materials. Perfect. Okay, so yes, one more comment that I'd like to make here. I'm already encouraging that you guys please use software tools wherever you can, right? So for calculations and whatnot, calculator को directly use करें, go for it. वो cubic equation को solve करने के लिए भी calculator को use करें. उसी तरह actually जब हमने एक tensor की eigen values ही निकालनी है, so let me just erase all of this. अगर हमें पहले ही पता है कि principal stresses जो हैं वो eigen values हैं, तो फिर हम ऐसा भी तो कर सकते हैं कि वही MATLAB या वही tools, I'm not sure कि calculator में eigen values directly निकलती हैं या नहीं. At least I never looked it up, to be honest. I should probably do that. मैं MATLAB use कर लेती होती हूँ just to find it. But my point is that we can use those same tools to directly find the eigenvalues या principal values of the tensor. ठीक? So that's also fine with me. So long as I don't, if I'm explicitly asking you to show the working, because it's important to know as well कि ये चीज़ कैसे आ रही है. ठीक है? So if I'm asking you to show the working, then you must use I1, I2, I3, solve the cubic equation to get to the principal values. But if I'm not, or ये ज़ाहिर है, all of these exams or whatever assessments that we're having in this online mode, it is open book, right? It's open book, you can look up things and so on. So you're welcome to just directly find the principal stresses or eigenvalues if I have not asked for the working. Okay? Or how can we do that? Again, the same old, this even matrix calc does it. So इधर ये देखें, इसमें eigenvalues calculator है, तो आप इसमें जाएं and you pop in your matrix and then click on find. It'll find us the eigenvalues. ठीक है जी. So we've solved, essentially we now know कि principal stresses or maximum shear stress कैसे निकालना है at a point, right? So I hope we're good with this. Now, just to demonstrate further, as we've been discussing, it's the failure which is determined by the principal stresses. whether it be ductile or a brittle material, because अगर हमने principal values निकालनी है तो उससे हम वो maximum shear stress भी निकाल लेते हैं, right? The point is कि इसी वजह से हम ये principal values निकालना चाहते हैं ताकि हम figure out कर सकें, हम analyze कर सकें कि कोई given situation में failure होगा या नहीं. और इसके लिए ना अब एक particularly important चीज़ आती है, which is a representation के how do we figure out कि failure हो रहा है या नहीं. Let me explain that further. So now clearly हमारे पास 3 principal stresses आ रहे हैं in 3D. ठीक. So अब हमें कैसे पता कि ये खाली sigma 1 important है या ये sigma 2 important है या sigma 3 important है? How do we know that? Like क्या करें? अगर ये stress state ज़्यादा important है या फिर कोई और जिसके अंदर we have 10, 200 और 2, let's say. इसमें मैं कैसे determine करूँ कि ये वाली stress state is more critical या फिर ये वाली stress state is more critical? Which one is going to lead to failure? Maybe perhaps हमारे पास एक ये point A है जिसके ऊपर ये stress state है. So this is the stress state at point A. Whereas I have another point in the body which is B. और B का ये sigma prime, by the way sigma prime नहीं sigma P कर देते हैं because they may be different orientations. इसकी principal direction शायद ऐसी हो, इस वाले की maybe कुछ और हो बिल्कुल ही, and so on. You get my point, right? कि the principal values मैंने दोनों points पे represent कर लिए हैं. And how do I determine कि using these 3 values, how can I figure out whether failure is occurring or not? Now, for that, we have this concept of defining effective stresses. मतलब ये कि by taking these 3 values and combining them up in some way, कि हमारे पास actually एक ही scalar value आ जाए और हम उसी एक scalar value को किसी criteria के तहत judge कर सकें. Then that is how we are able to determine failure using these 3 different or 3 principal values basically. And the most commonly used measure of effective stress is known as von Mises stress. And I'll just show you what it is. It was posed by the guy called von Mises and hence the name. So von Mises ने किया क्या था? उसने ना कहा था कि मैं एक वैल्यू, एक स्केलर वैल्यू फॉर स्ट्रेस स्टेट डिफाइन करने लगा हूँ जो कि ये है. ठीक है जी. और इसलिए मैंने इसको सिग्मा वॉन मीसिस का नाम दिया है. और व्हाट इट कंटेन्स इज इट कंटेन्स आर 3 प्रिंसिपल स्ट्रेसेस इन सम कॉम्बिनेशन क्लियरली. And what the combination is, if you look closely, it's the difference in the first 2 principal stresses squared, difference in the next 2 principal stresses squared, and finally the difference between the वो जो आखिरी combination रह गई थी उनका difference squared. Please notice कि because वो square हो जाएगा, so it doesn't actually matter कि आप किस order में उनको subtract कर रहे हैं. ठीक. So this is stating basically कि ये जो मेरे पास sigma 1, sigma 2, sigma 3 की principal values आई हैं, और ये भी zeros होंगे, उन तीनों को यूज़ करके हम एक वैल्यू डिफाइन कर लेते हैं, एक वैल्यू, एक नंबर कैलकुलेट कर लेते हैं फॉर दैट पॉइंट, एंड दैट इज़ नोन एज द वॉन मीसेस स्ट्रेस, और उसकी एक्सप्रेशन इज़ गिवन राइट हियर. एंड देन व्हाट वी आर एबल टू डू इज़ कि जैसे हमारे पास ये 2 पॉइंट्स थे इन द बॉडी एज आई हैड बीन डिस्क्राइबिंग कि ये पॉइंट ए एंड पॉइंट बी है, point A and point B, then what I can do is I can find ये 3 use करके I can find the sigma von Mises for A and I can find the sigma von Mises for B. ठीक है, एक वैल्यू आ जाएगी दोनों की. And clearly I think, I hope you all can identify कि failure will be more likely whichever von Mises value is larger, right? Because that will be a more critical stress state. उसमें sort of loading ज़्यादा हो रही है. It's a higher loading state essentially. Or further to that, the value that we compare the von Mises stress to is something जो I think मतलब सबसे obvious चीज़ that you can think of. It's the yield strength of a material. So that is, ये yield strength तो हम सबको maybe थोड़ा थोड़ा चलें, सबको नहीं याद होगा maybe. If you have a ductile material, then it has a stress strain curve that most of the time looks something like this, right? Ductile material का. तो जिधर से उसकी plasticity शुरू होती है, this is its yield strength, right? Sigma ys, yield strength. So what we tend to do when we are trying to determine failure in a 3D stress state, इसके हम यही yield strength को use करते हैं और इसके against von Mises stress को compare कर लेते हैं, right? और अगर हमारा at a given point in the body the von Mises stress is higher than the yield strength, then we say that there will be failure occurring. Now I forgot to mention one very important thing, which was that this effective stress measure or the von Mises stress is defined primarily for ductile materials. ठीक है जी, ये failure criteria, मतलब ये वॉन मिसेस को यील्ड स्ट्रेंथ के अगेंस्ट कंपेयर करना जो है ना, वो सिर्फ और सिर्फ हम डक्टाइल मटेरियल्स के लिए ही करते हैं, ओके, नॉट फॉर ब्रिटल मटेरियल्स. एक तो फर्स्ट ऑफ ऑल द रीज़न बीइंग के प्लीज़ नोट के वो यील्ड स्ट्रेंथ के अगेंस्ट कंपेयर हो रहा है, राइट? यील्डिंग होती ही किस में है? डक्टाइल मटेरियल में. ब्रिटल मटेरियल तो इस तरह का कर्व ही नहीं होता उनका, राइट? उनका स्ट्रेस स्ट्रेन प्रोफाइल इज कम्प्लीटली डिफरेंट. So this von Mises stress or von Mises yield criteria is it's a yield criteria. It's a plasticity criteria. Okay. Or this leads me finally to give you an example के I'm sure आप लोगों ने बहुत I'm sure कि आप लोग खुद बहुत simulations करते हैं, and you might have noticed कि I already हम लोग stress state को देख रहे हैं कि अगर मैं XYZ coordinates के अंदर define करूँ, तो मेरे पास so we have so many stress components, right? Sigma 1 2, sigma 1 3, sigma 2 1, sigma 2 2, sigma 2 3, sigma 3 1, 3 2 and 3 3, right? और there are so many of them. तो अगर मैं कोई एक वो जो बॉडी मैंने ली थी और मुझे विजुअली इसको दिखाना है कि एट अ पॉइंट इसके डिफरेंट पॉइंट्स पे क्या स्ट्रेसेस हैं, सो मैं ये पूरे स्ट्रेस स्टेट को कैसे दिखाऊं? या तो एट एनी वन टाइम आई कैन जस्ट शो सिग्मा 1 1 या ओनली शो सिग्मा 1 3 या ओनली शो सिग्मा 3 3 एंड सो ऑन. तो मुझे तो इतनी सारी तस्वीरें चाहिए होंगी, इतने सारे कॉन्टोर्स चाहिए होंगे एंड सो ऑन. If that is important to us, that is if each of the individual stress components are important to us, then that's fine, we'll plot all those stress contours. But अगर हमारे पास सिर्फ एक overall loading important है खाली, तो फिर आम तौर पे हम क्या करते हैं, and this is the default value which is set for most finite element software such as Abacus, ANSYS, SolidWorks, what else, COMSOL and so on, then the default value that gets plotted is this von Mises stress. Exactly because इससे हमारे पास सिर्फ एक वैल्यू आ जाती है जिसमें हमारी ये सारी वैल्यूज incorporated होती हैं, right? Or we can then show the stress state at a point. So as just an example, ये ANSYS का कोई एनालिसिस है फॉर ए गियर, 2 gears in contact with each other. So उसके अंदर इफ़ यू नोटिस के वही बात ना कि ये ब्लू और ये ऑरेंज और ये ग्रीन का मतलब क्या है. अगर मैंने स्ट्रेस कंपोनेंट्स प्लॉट करने हो तो वो तो मेरे पास इतने सारे हैं, मेरे पास लाइक टोटल 9 कंपोनेंट्स, जिसमें से 6 are independent. So which one am I plotting? अगर मुझे शो करना है कि यहाँ पे ज़्यादा लोडिंग है. So most of the time that the one that we plot is the von Mises stress as shown right here. Okay. So yes, yeah, and that was from ANSYS. This one I taken from COMSOL. So again here as well, it's just the von Mises stress which is being shown as a effective stress measure. Just one scalar value जो पूरी stress state को incorporate कर दे. Right. So that was it for stress ka part for our course. Now 6:15 we have our quiz. It's okay. I'll give you guys a few minutes break. So 6:15 पे वो it'll pop up as you know.